I'm Kunihiro Ito from NEC. I talk about our privacy protection algorithm for machine learning. These days, there is increasing concern on privacy of sensitive data. To obtain machine learning models, we use various domains such as healthcare, finance, natural language, and autonomous driving. According to recent privacy guidelines like GDPR, machine learners have to protect privacy of training data. A specific threat is membership inference attack, which is an attempt that infer whether a target data is used as a training data or not. Adversary queries the target to a machine learning model to get output confidence score and observe it, infer if the target is in the training dataset or not. Such leakage of membership information can be a threat when training data is collected from sensitive domain, like patient of cancer. Membership inference attack is mainly caused by overfitting, that is, tendency of machine learning model excessively run the training dataset. For instance, there are gaps between confidence score of training data and that of non-training data. So adversary can exploit this to infer membership information. There are two kinds of defenses. Certified defense. Their algorithms give some guarantee, but nobody knows they have optimal privacy utility trade-offs, especially under real-world settings. Empirical defense. Their algorithms have no guarantee, but not bad if designed properly. Empirical defenses are often either broken with some attack or proved to be an optimal defense in the future. So inventing empirical defenses that use different fundamental principles is important. State-of-the-art empirical defense prevents overfilling by distillation with public data. First, train teacher model using private training data. Prepare another public data to obtain soft score using that data. Then, relabeling data set and train student model. The resulting model is protected since the student learns the moderate confidence effects of public data. And utility is also kept, that is, benefit of distillation. Cool. But there is a difficulty. How to obtain public data from the same domain with private data? We propose a solution. Here is a comparison between proposed defenses and existing schemes. Proposed defense and state-of-the-art defense DMP have the same level of privacy utility trade-off. Nonetheless, proposed defense doesn't require any public data. Okay, to introduce proposed defense, we begin with two basic ideas. First idea, using private data again instead of public data. First, train teacher model by training data. Copy training data. Use them as alternative of public data for distillation. But this idea fails since overfitting remains. Students learn extreme confidence score effects of training data. The second idea, reading a part of training data aside and treat them as a public data. First, split training data. Train teacher model by using one part, and train student model by another part. Software will have a moderate confidence, so resulting model is protected. Cool. But inevitably decrease utility due to small amount of training data. Okay, combining the above two ideas proposes defense. Knowledge class distillation is stated as follows. Divide the training dataset into an disjoint subset, BI. Train teacher models, FI, by complement sets of DI. Obtain software levels FI of X for X in DI. And finally, train student model. The resulting model is protected since soft scores with moderate confidence are obtained by data DI, which are not used for training the teacher models. Also keeping utility since the amount of data used for training teacher models are asymptotic to that of original training data, as number of dataset partition N increases. We have training trade-off control for privacy and utility. The parameter alpha in loss function controls how much student runs soft level and true level. For instance, alpha equals to 1 means full defense, and alpha equals to 0 means unprotected. Okay, we conduct experiments on 3 benchmark datasets, Cipher, Texas, and Purchase, through 2 metrics, test accuracy and attack accuracy, against 2 kinds of MIA, metric-based and not neural network-based. Here is an overview. Firstly, KCD is the best among defense that doesn't use public dataset. KCD is the only defense achieving high utility and low MIA risk. Secondly, KCD is comparable to the state-of-the-art defense that requires public dataset. Both have a high utility and a similar privacy level. Nonetheless, KCD doesn't require any public dataset. To state more concretely, we conduct comparison experiment on various trade-off parameters. Here, x-axis means utility, y-axis means MIA risk. So bottom right is preferred. At left figure shows KCD is superior to existing defenses that requires not using public dataset. As right figure shows, KCD is comparable with DMP that uses public dataset. We conduct further experiments to understand how KCD protects machine learning models. KCD is composed with 2 techniques, splitting and reusing dataset. We examine the cases where one of them are missing. First scheme, reusing DMP. Train teacher model, copy training data, use data percent of training data of them as alternative of public data. This is equivalent to KCD without splitting technique and can be seen as DMP that uses private data again instead of a public data. Second scheme, splitting DMP. Split training data with ratio data. Train teacher model by using one part. Then train student model by another part. This is equivalent to KCD without reusing technique and can be seen as DMP that leaves a part of the training data aside and treats them as public data. We conduct experiment on various data. Figure shows KCD is superior to reusing and splitting DMP. So both splitting and reusing techniques are necessary for KCD. Conclusion. We proposed novel MIA defense that does not use public dataset through splitting and reusing techniques on training dataset. Experiments show that KCD is the best defense among existing schemes that doesn't use public dataset and even is comparable to the state-of-the-art defense that requires public dataset. That's all. Thank you.